Hello, I'm Julian Panetta, an assistant professor at UC Davis. Today I will be presenting our work entitled Computational Inverse Design of Surface-Based Inflatables. This project was a joint work with Florinus Varanu, Tim Chen and Mark Pauly at EPFL, Emmanuel Seifert at Hebrew University of Jerusalem, and Benoit Roman at PMMH. Fusing together two sheets of material along a network of parallel curves creates pockets that inflate into tubes when pressurized. If the fusing curves are not all perfectly straight, this inflation process has the surprising side effect of deforming the sheet out of plane and into a doubly curved 3D shape. The final shape assumed by the inflated sheet has high stiffness, making this material system a promising approach for rapidly fabricating and deploying curved surface structures. However, the non-trivial relationship between the shape and topology of the fusing curve network and the resulting inflated geometry makes for a challenging design problem that can only be solved effectively using computation. In fact, we have found that an effective design algorithm must combine insights from differential geometry with accurate physical simulation and sensitivity analysis. This design algorithm is the focus of my talk today. Numerous recent works in graphics, mechanical engineering, and computational fabrication have focused on creating structures that can deploy from flat, easy-to-fabricate configurations into curved 3D surfaces. These projects have exploited a diverse array of material systems and physical phenomena to program the desired shape into the fabricated object. The surface-based inflatables we design are motivated by the same basic goals, but offer some key practical benefits and raise some unique computational challenges. Also closely related to our work are computational design tools for balloons and pneumatic objects. The Aeromorph project in particular introduces parametric hinge mechanisms that can be used to make a sheet bend or twist into 3D under inflation. These hinges are based on the same underlying physical mechanism as our inflatables, but an automated inverse design algorithm for approximating smooth target surfaces is not yet available. Some benefits that surface-based inflatables offer over previous types of deployable structures are their ease of fabrication and deployment, their structural performance, and their rich shape space. All of our prototypes were fabricated with what is essentially a modified laser cutter, tuning the laser to weld the sheets together rather than cut through them. The design is then easy to deploy and retract with an air pump and does not require precise pressure control. Once inflated, our structures are stiff, lightweight, and importantly do not require pressurization of the enclosed space. This enables the design of architectural surfaces with openings. Finally, we are able to produce structures with negative mean curvature, which is impossible with traditional balloons unless additional interior strings are attached. For instance, the negatively curved indentation at the top of this LILIUM tower example had to be flattened for fabrication with the programmable exetics approach, whereas it could be closely approximated by an inflatable. An essential prerequisite of our design algorithm is to accurately and efficiently simulate the inflation process to evaluate candidate designs. We pose the simulation problem as a minimization of a total potential energy that incorporates the elastic potential energy stored in the fused sheets and the work done by the pressure forces. For the elastic energy term, our sheet's extreme thinness allows us to neglect bending forces, retaining only a membrane energy term described by an energy density function, psi. Since our sheets are nearly inextensible, we found the precise choice of material model not to significantly influence the inflated shape. However, it is important to properly model the tendency of the thin sheets to wrinkle under compression rather than resist it. Following the approach proposed by Melina Skouras and her colleagues in 2014, we use an incompressible neo-Hookean energy with a tension field theory relaxation for psi. This tension field theory approximation simply neglects any elastic energy contributions arising from compression, as they would be released by wrinkling of the sheet. The resulting coarsened material model allows us to accurately simulate the inflated shapes without the high-resolution meshes that would be needed to resolve the fine wrinkling details. We discretize the elastic membrane with a triangle mesh and use piecewise linear finite elements to represent the deformation map. The simulation operates on two copies of the mesh, one for the top and bottom sheets. The sheets are fused together by assigning the same deformation variables to each copy of the fusing curve vertices, highlighted here in blue. We solve the resulting discrete minimization problem using Newton's method. Using this physical simulation, we can pose our design problem as minimizing the deviation between the inflated shape and the target surface. However, it is not obvious how to optimize over the diverse space of fusing curve patterns with different topologies and shapes. We will use gradient-based optimization to tightly fit the inflated structure to the target, but to be effective, this requires a reasonably good starting point and crucially a known curve network topology. To obtain this initialization, we consider a geometric abstraction of the inflation process that directly leads to an approximate solution to the inverse design problem. To develop this geometric abstraction, let's return to the inflation of the straight tube design and study the deformation it applies to the sheet. Focusing on a single tube, we see that, as it inflates, it contracts in the transverse direction by a factor of pi over 2. At the same time, the length along the tube is essentially unchanged. The combined effect of all of the tubes is to contract the full sheet's width by some factor alpha, whose exact value depends on the ratio of the fusing curve width d to the unfused material width w. Lower and upper bounds for this contraction factor are determined by practical considerations such as the diameter of the fusing laser spot. If we draw non-straight fusing curves, individual tubes still approximately contract transversely by alpha and preserve lengths along the tube. The only difference is that now the directions of contraction vary. We can therefore take an abstracted, homogenized view of the inflation process as changing distances between points on the sheet and effectively assigning a new metric to the sheet. If the new metric spatially varies, it can force the sheet to assume a shape with non-zero Gaussian curvature. In this homogenized model, we can represent the inflation as a mapping from the flat sheet in the 2D plane to a surface in 3D. Our insight about the tube's anisotropic contraction behavior can be formulated in terms of this mapping. Specifically, the singular value decomposition of the mapping's Jacobian must take the following form. This simply says that the map preserves lengths along the tube directions phi and contracts the transverse lengths by an admissible factor alpha. We now understand the space of maps F that correspond to a feasible inflation of a flat sheet into a 3D shape. To solve the inverse design problem, we seek a flattening of the surface that looks like the inverse of one of these maps. This now sounds like a classic problem from computer graphics, computing a surface parametrization. However, existing parametrization algorithms typically seek maps that minimize distortion. We instead wish to find a flattening that distorts the surface in a way that perfectly corresponds to an inflation deformation. In other words, one of the Jacobian singular values should be 1, and the other should lie in the admissible range. We can compute a flattening in this form by minimizing the following objective expressed as a simple function of the singular values. This objective fits the smaller singular value to 1 and the larger singular value to the admissible range. Notice that the principal stretches sigma of the flattening map should be the reciprocal of the inflation contraction factors alpha, and so the bounds for sigma are just the reciprocal of the bounds for alpha. This energy can be minimized easily and robustly using a local global iteration very similar to the traditional ARAP algorithm. And in fact, this has been done before in the literature on inverse design for pneumatic elastomers. Pneumatic elastomers exploit a similar anisotropic contraction behavior as our inflatables, leading to essentially the same parametrization problem. In fact, for special classes of input, for example surfaces of revolution, closed-form expressions have even been derived for the spatially varying contraction directions that encode the surface's Gaussian curvature. However, the existing approaches have two main issues. First, the local global algorithm produces very noisy tube direction fields, through which it is unclear how to trace continuous fusing curves. And second, considering only the metric distortion of the inflation mapping, as done by the singular value fitting objective, misses critical aspects of the physical system. Specifically, it ignores how much tubes must bend to follow the surface. We address the first issue by adding regularization terms that promote smoothness in both the direction and stretch factor fields. We note that even with these regularizations, we are still able to produce maps that tightly adhere to the singular value constraints. To tackle the second issue, we first clarify the problem by investigating what happens when we inflate a design created with the purely metric-based approach. Even if we force the sheet to initially lie on the target surface, it immediately deforms into a very different shape. Fixing the boundary helps, but still the surface approximation is quite poor. What we are seeing is actually not a failure of the parametrization to robustly encode the target surface's curvature. We can confirm this by solving for an immersion of the flattened sheet with the same metric used to generate the tube patterns. We see that this immersion does faithfully approximate the shape. Looking more carefully at the inflation deformation, we notice that the long tubes traversing the ridges of the target surface want to unbend as they inflate. As this unbending fights the desired curvature encoded in the sheet's metric, we must discourage the tubes from aligning with these directions of high normal curvature. To penalize this unfavorable alignment, we add another regularization term to our parametrization energy that is inspired by a homogenized model of bending beams. At each point on the target surface, we imagine an infinitesimal beam that bends to follow a geodesic along the local tube direction. The bending energy stored in this beam is proportional to its squared curvature. For the beam to adhere to the surface, its curvature must equal the target surface's normal curvature along the tube direction v, which can be computed using the shape operator s. Integrating this bending energy density over the surface obtains an energy proportional to our bending regularization term shown here. We note that the tube directions v are really just the right singular vectors of the parametrization's Jacobian. As the target surface is constant during the optimization, S can be represented by a constant symmetric matrix field over the target surface that we pre-compute. This makes our bending energy simply a quadratic function of the right singular vectors. With this added term, tubes redirect to avoid traversing the ridges, and the sheet inflates into a much closer approximation of the target surface. Here we compare a result generated using this bending energy term against the original design that only accounted for metric distortion. We see that the surface approximation is significantly improved. Our full parametrization energy accounting for both intrinsic and extrinsic curvature of the target surface is given here. We optimize this energy with Newton's method and discuss our strategies for initialization and coping with the energy's non-convexity in our paper. The fields of singular values and singular vectors from our parametrization tell us the desired fusing curve orientation and width at each point on the flattened sheet. We draw roughly evenly spaced fusing curves that align with the tube direction field and adjust the wall widths according to the stretch factors. For this, we adapted Keenan-Crane's stripe patterns code. Our parametrization-based inverse design approach obtains an initial design that can do a fairly good job of approximating the target surface, but there is still a large room for improvement by a true physics-guided optimization algorithm. Now that we have determined a fusing curve topology and have a computational mesh, we can pose the design problem as an optimization of the mesh vertex positions. Denoting the inflated equilibrium deformation as phi star, we minimize the distance to the target surface. We further include additional penalty terms to maintain a high-quality simulation mesh. The collapse barrier term here prevents triangles from degenerating during the optimization, and also prevents the fusing curves from shrinking below the laser spot diameter of the fabrication machine. An additional smoothing regularization term prevents the fusing curves from becoming significantly more jagged during the optimization, and promotes roughly uniform spacing of the fusing curve vertices. Please see our paper for specific formulas for each term and details on the sensitivity analysis used to efficiently compute gradients with respect to the design variables. Instead of optimizing all vertex positions, we optimize the positions of only the fused vertices highlighted in blue. We then smoothly interpolate these positions onto the interior vertices to preserve high triangulation quality of the sheet mesh. For nearly all examples, this was enough to maintain a high-quality mesh. We describe in our paper an automated remeshing process that was needed for two examples where a large movement of one of the fusing curves badly stretched some of the mesh's triangles. This animation visualizes the iterations of our optimization algorithm running for the LILIUM tower. The color map used on the right visualizes the distance to the target surface. Our algorithm is able to fit the inflated structure closely to the design surface. While the changes to the initial curves made by the optimization are often fairly small, the improvements to the surface approximation are substantial, and it would be impossible to achieve them without computational assistance. Here is our optimization algorithm running on two more target surfaces. This figure compares the designs for the LILIUM tower before and after our physically guided shape optimization stage. The histogram shows a significant reduction in the distance to the target surface after optimization, and visually we see the optimization was able to correct for collapses in the design's lobes and much better approximate the indentation at the top. We have now described all steps of our inverse design pipeline, which I will review here. Starting from an input surface, we flatten it to the plane using our parametrization algorithm. We then extract fusing curve directions and widths and use these to generate an initial curve layout and simulation mesh. Finally, we simulate the design's inflation and run our shape optimization to tightly fit to the input surface. The final result indeed inflates from a flat sheet into the target shape. I would now like to show some more results and potential applications of our design tool. Here is an inflatable helmet design that shows we have the freedom to vary the tube sizes while still approximating the intended shape. Another use case we envision is an inflatable cast adapted to a patient's specific geometry. We are also able to approximate detailed surfaces like this face mask, which we see inflating here from its flat state. We fabricated several prototypes generated by our algorithm using a custom machine consisting of a laser mounted on a CNC plotter. We used 75 micrometer thick polyethylene film as the sheet material, and the machine is capable of fusing designs up to 1.3 meters by 1.3 meters. Here are some of the architectural surface style prototypes we fabricated. Many of our examples were designed with their boundaries anchored to fixed points on the ground for more robust shape approximation. However, we emphasize that the enclosed space is never pressurized, so open doors or windows could be inserted without deflating the structure. We also fabricated the face mask example, which you can see deflate here. We scanned the inflated models using photogrammetry software to compute quantitative error metrics. We show here the scanned prototypes colored by the distance to the target surface. We found the deviations from the target surface were usually within 2% of the bounding box diagonal. I will conclude with some observations on our current method and some opportunities for future work. First, I would like to re-emphasize the roles that both our geometric abstraction and the detailed physics-based optimization play. Neither on its own could produce high-quality results. Second, I will note that not every surface can be fabricated with this technique. In future work, we would like to better understand the space of achievable shapes and experiment with how to expand this space by inserting cuts and singularities during the flattening stage. Finally, while our results generally exhibited good stiffness in our experiments, we would like to explicitly optimize the surfaces for even greater stability and to account for custom loads. We would like to acknowledge the Swiss National Science Foundation and the NCCR Digital Fabrication Initiative for funding this research. Thank you for your attention.